Hi, I'm Mike with NI, and I'm joined by Saravana from Soliton Technologies. And today we'd like to talk to you about how you can improve the process of validating your digital interfaces to make sure they're in compliance with industry standard protocol specifications. Today we're going to focus on the MIPI I3C protocol, but the tools that we introduce will be useful and compatible with a number of different protocols in addition to I3C. So first off, we'll start with a little bit of an overview of our companies. So NI has been in the semiconductor validation space for more than 4 decades, and we deliver high-performance instrumentation and software that helps our customers accelerate productivity and get to market more quickly. We also have other solutions for other industries as well, but my focus is on the semiconductor space. And we've gone through an evolution over the past few years, moving from a product provider where it was up to the customer to integrate those products together for a solution, and moved more towards a solution provider where we're working with companies like Soliton to develop turnkey software solutions that work with our high performance instrumentation and base software to give you a solution that is closer to the job that you need to do, which is one of the examples we're talking about today, digital compliance testing. Now, we are both MIPI Alliance members, and Saravana, if you'd like to give a quick introduction to Soliton.
Thanks, Mike. Yeah, so to talk about Soliton, so we help semiconductor companies to build the automation software. We are in this field for almost 20 years from now, and we have a wide experience with working with multiple customers across the semiconductor industry. So we engage customers and help them to build right from single device bench level projects to organization wide standardization engagement. So we help customers by providing out-of-box products like protocol validation solution, which we're gonna talk about it later, and the LD and other solutions like LDO measurement tools and more solutions. So also we help customers in helping to build custom software development. So we, with our experience, we have helped 3 leading semiconductor organizations to drive organization-wide standardization, and we have engaged with more than 75 BU level projects with the leading semiconductor companies. So recently, last year, we have signed the strategic partnership with NI to jointly develop bench enterprise software for semiconductor validation, automation, and spec data management. So I'll hand it over back to Mike.
Yeah, thanks, Saravana. And this partnership with Soliton isn't new. We've been working with Soliton for more than 2 decades. We've recently just more formalized the partnership to co-develop solutions together. In addition to protocol validation, like Saravana mentioned, we have solutions for spec management and data management that we're co-developing together as well. We're also both MIPI Alliance members, so that is something that we both have in common, and we have a lot of experience working with MIPI on these types of protocol standards. So let's go 1 slide forward. So working with semiconductor validation customer, we see really common challenges that persist across the whole industry. Obviously, our devices are getting more complex, which drives new measurement capabilities and new device capabilities. In order to keep up with those changes while getting to market more quickly, semiconductor customers are looking for new and innovative ways of performing measurements and performing device validation tasks. They're also looking to break down or further break down the silos that might exist between design and simulation and verification through to post-silicon validation and characterization, and all the way through to production test, things that will help with requirements and specifications tracking and data management, not just within the silo of one of those spaces, but across the entire life cycle. We've also seen challenges with finding ways to reuse measurement IP so that you're not duplicating efforts across your teams or across your BUs or organization. And when you have different solutions that were developed separately, they may not produce the exact same results, and so it may be difficult to compare the data across teams in a consistent way. But we have seen some common tactics used to combat these challenges, and it starts with standardization or some amount of standardization for both hardware and software. If you have that common layer that allows you to reduce the amount of time that you're doing developing your tools, and it also helps increase the likelihood that you can reuse measurement IP across your different groups. This will also lower the barrier and lower the cost of reproducing and deploying systems globally. And ultimately, at the end of the day, it's all about data and being able to make data-driven decisions on your product and giving your lead customers early access to that data. So that's ultimately the end goal here. So with those challenges in mind, Soliton and I have been working on a number of different turnkey software solutions that work with NI high-performance PXI instrumentation for some of the most common digital tasks within semiconductor validation. And the first one, which we released last year, is the semiconductor device control software. And this is something that is core to every single validation bench in the mixed signal IC space. One of the most common tasks that you have to do when validating these devices is to communicate to the part using a standard protocol or a proprietary protocol, and then being able to do some register read writes or static DIO operations for controlling load board or eval board elements like relays. And so we were really excited to bring that to market. And in addition to that, we also have other solutions that Soliton has developed for things like protocol validation and protocol analyzer. So the protocol validation solutions was one of the key things that we're going to focus on today. And this is a turnkey software solution for testing the compliance of a digital interface against an industry standard digital protocol, such as MIPI I3C. And the software does work with other protocols as well, but we chose to focus on I3C today. The software has built-in capabilities to test things like compliance with timing, electrical, functional, and even fault reliability tests as well. And so we're really excited about that, and you'll hear more about that in a moment. We also have a protocol analyzer that Soliton developed for that works with NI oscilloscopes to decode, digital protocols and digital waveforms that you're capturing with your oscilloscopes. So together, these solutions provide more higher level starting points or turnkey solutions that you can use out of the box with NI instrumentation. So I'll go ahead and hand it over to Saravana to dive into that center product, the protocol validation solution, where you'll learn more about our capabilities for I3C. You'll learn more about the protocol and what's unique and new about it, and what type of benefits that it provides for you as the chip designer, and what our solution can do to help validate that. So Saravana, go ahead.
Yeah. Thanks, Mike, for the brief intro. So let's jump into the protocol part of the session. So as we know already that semiconductor chips are becoming complex and powerful in the recent days. Day by day, things are getting complex. We are trying to improve the performance, improve the feature set of the semiconductor chips. This has led to the need for the upgrade in digital communication interfaces. We would like to have less number of wires. We would like to have low power protocols, interrupt capabilities, and much more on other advanced capabilities. So this has constantly driven the need for upgrade in the digital protocol interfaces, and MIPI as standardization organization helps in building or in creating the standardized protocols for different segment of the industry, for like control and data, multimedia, debug and trace, and inter-process communications. So for this part of the session, we would concentrate only on the control and data part of it. So under the control and data segment, we have three commonly used protocols. The first one is the MIPI I3c protocol, which is a medium speed protocol mainly used to communicate between the peripherals and the application processors in the mobile and IoT industry. The next is the MIPI system power management protocol, which is commonly called as SPMI protocol, which is used for power management between the SoC and the peripheral chips. And the third one is the MIPI RF front-end control interface, used to integrate the RF front-end devices with the controller. So these are the common set of protocols that is available and used by the users under the control and data segment, and there are much more protocols from MIPI. So from here on, we will more focus into the MIPI I3C protocol for the rest of the session, and take I3C as an example to showcase our validation product as well. So moving on. So what is MIPI I3C protocol? So MIPI I3C is an improved integrated circuit. So in the industry, generally there was a need for a consistent, flexible, low power two-wire protocol for ever expanding sensor manufacturers. So the day by day, the number of sensors, the type of sensors were growing, and the system started using more number of sensors, and there was a need to use a common interface to have all the sensors connected. So that has led to the evolution of the MIPI I3C protocol. So MIPI I3C protocol supports up to 11 target devices in the bus, and of course these are the certain types of devices that can be in the I3C bus. It can have I3C controller, secondary controller, target devices, and it's obvious that I3C is an improved version of I2C, and it is backward compatible with I2C protocol. So it supports having I2C target devices in the bus. And moreover, it is a multi-drop and multi-controller type of protocol that supports advanced features like interrupts, group addressing, and much more. So in the next few minutes, we will see what the more important features of I3C protocol, which makes it more powerful protocol than the conventional protocols. So the first one is the data transfer mode that the I3C protocol offers. So it offers 3 different modes of operation. One is the I2C mode, the I3C single data rate mode, where data one clock is used to send one particular data, and we have the I3C HDR mode, which has internally 3 different modes: dual data rate mode, where for each clock edges we would send one data; ternary assembling modes, bulk transfer mode, where we will send data parallelly through multiple data lines. So the advantage that these modes offer is mainly on the data transfer speed. For the same clock frequency of 12.5 MHz, you could see on the image on the right hand side where each mode is offering a different data transfer mode, and the data transfer speed is getting increased between the modes right from SDR and HDR mode. And also we could see the comparison between these data transfer speed that we get with the conventional I2C protocol and what I3C offers over the I2C protocol. There is a huge advantage gained over here, which makes it a default candidate used for medium speed applications. There are certain other features that are making the protocol powerful apart from the data transfer speed. One such feature is the target addressing process. So typically, if you look at a protocol interface, you would need a separate wires to address the device. But I2C and protocols like I2C has a concept of assigning an address to the device so that the extra wires can be eliminated. Extra pins and wires can be eliminated to talk or address to a device. So I3C has one more feature on top of that. So there could be in a system there could be multiple devices, sensors which could be monitoring a critical process, and there is a sensor which could be monitoring a lighter process. And the sensor that monitoring a critical process should have given higher priority whenever it needs to talk to the controller or to interrupt. It needs high priority so that critical information is passed in the first rather than passing the low priority information. So in order to keep the priority, I3C allows the controller to assign a dynamic address to each devices in the bus based on its characteristics and type. And using that address, we can have the priority established with the value of the address. So that's one important feature that makes it more powerful and advantageous. And we have few more features like in-band interrupts, which helps the device to interrupt the I3C controller if it wants to send an high priority information. So for example, in conventional protocols like I2C or SPI, if the target devices wants to send an data to the controller, it will not be able to do that unless controller initiates a transaction and asks for any information from the target device. So this IBA mechanism offers a certain way to the target devices that can be used by the target devices to interrupt the controller. And controller also has the flexibility to either respond to it or disable it or reject it. And the Hardside mechanism is one another important feature that everyone would like and make the I3C protocol as an attractive one. Say in a system there would be multiple devices on the board, and it is not a strict requirement that all the devices should be powered on and participating in the bus transaction in all the situation. Certain devices can be in power off state, or it can be in low power mode, and will not take part in the bus communications. So at certain point of time, they will come into the bus for certain use cases. And when they join the bus, it needs a dynamic address so that other devices can talk to it. So it has a way to interrupt the controller to assign a dynamic address to itself. So the way of requesting the address assignment process is called as Hardside mechanism. And the controller again has the flexibility to respond to it, disable it, or reject it. So that's one attractive feature of I3C protocol. And few other features like controller clock stalling, where controller can stall the S clock low period. So this is mainly to synchronize the absolute and relative timing of the message. And in certain use cases, controller needs to internally synchronize the data before giving it to the IOs. So it can use this stretching period to synchronize the data and send it out. There is another powerful feature called bus handoff between the controller and target, especially during the acknowledgement bit and T bit. This is mainly used to make sure the data is transferred properly, and also to understand whether the device has enough data to continue the transaction, or the device is willing to terminate the transaction. With this, controller and target can easily continue or easily know whether to continue or terminate the transaction, and reduce the transaction length. And one more important feature that I3C protocol offers over all the other protocols is the common command codes. So typically in a protocol environment, if you want to configure a device to go into a certain settings, we will typically note down certain registers from the data sheet, use that registers, write some value to the register. We will calculate the bit fields and write the values, and then that will set the device settings. But I3C offers common command code set, which is by hex values assigned to each code, and the user can send that code and a payload to it, and all the device configuration is done internally. So this common command codes, it can be sent either in a broadcast mode to all the devices in the bus, or it can be directed to a specific device. And and there is some need for reset also to be done in the bus. Say whenever something is not working well, the device should be reset. And in the conventional protocols, there is no other way to reset except power on reset. But with I3C, we have this powerful feature called target reset, where the controller has capability to reset the certain peripheral of the target devices, or the entire target devices together. So this helps in restoring the resetting and restoring the target devices in between the transaction errors or things like that. And there is another feature called device to device tunneling, where the devices can transfer data between itself without involving the controller device in the bus, so that the number of traffic in the bus is getting reduced. So these are the certain set of features which makes this protocol advantageous over the conventional protocol, and making it as a right candidate to adapt in across multiple domains going forward. So with this, we have seen the important features of the protocol. Let's see it from the validation engineer's point of view. So say now we have this MIPI I3C interface in our chip. So we need to validate the interface, right? So why should we validate? We need to say our chip is of good quality, it is interoperable with other devices, it is compliant with the spec. And what should we validate? So what a validation engineer will focus on is based on the protocol specifications. We have to validate the different features on the protocol, like the different modes of operations, different protocol features, functional tests by doing a Hardside test, or IBA test, or register read rates, fault recovery test, timing validation, electrical I/O parameters, where you sweep the timing or voltage parameter and see where the device fails, and see if it is working through the full range, full frequency range, and things like that. So these kind of things user has to make sure before releasing the product to the market. And recently MIPI has launched CTS, which is complaints test suite, which has an set of test cases that user can use to validate the devices to make sure it is interoperable on top of all these tests that we are providing. We need to validate. So this, although the I3C protocol has a lot of features and which makes it more powerful and advantageous, it also brings in the burden of validating a lot of features to make sure it is of good condition. So what would a validation engineer do if he needs to validate the I3C protocol interface? So based on our experience with the industry, typically we have seen two different approaches. So the first approach is the validation engineer will buy an protocol emulating devices like a protocol exciser or analyzer from the market, a box type instrument, or he can develop his own protocol emulator using a microcontroller or the FPGA, and write a simple piece of software on top of it to help user to control the protocol interface. Then he uses that to talk to the device, uses oscilloscope to capture the signals, do the measurements, and create reports manually. The pain point here is the overall process of bringing up the setup, the basic setup itself would take around 1 to 2 weeks, and it would take 3 to 5 weeks to validate each DUT. And moreover, user has to well versed in the protocol specification and has to do all the things on his own, and it's a cumbersome job. And with the protocol analyzers or exercisers with the available in the market, it's difficult to get the complete specification coverage, especially doing a timing validation. So this has led users to start using ATE based solution. Certain users are using ATE based solution, reading the protocol specification, developing patterns, and use ATE to talk to the device, get back the result, analyze the result, and post-process and take the report out of it. But the pain point again with ATE solution is like the user needs to have a deep familiarity with the protocol as well as the ATE platform, and ATE involves an intensive technical effort where user has to create the pattern files, analyzing the data captures, and moreover ATEs itself are a costly testers and costly solution, and does not have an user-friendly interface that helps user to quickly do the protocol testing, even though it offers the speed and resolution of the validation. So what we are trying to do, or what we are trying to provide user that can overcome these pain points, or we are trying to change the workflow of the protocol validation itself. So we are offering an ATE class protocol validation system on a benchtop instrumentation stack using NIPXI stack. So here we offer a powerful software which contains easy to configure GUI with debug features. It helps the user to do the configuration with ease with its GUI richness, and the user can also run automated tests using the software. And the software takes care of getting the protocol, building the protocol waveforms using the NI hardware stack. So the protocol specification is taken care by the software internally, and while the test is running, the software talks to the device and get the response, and based on that it reports the results to the user. So from the validation engineer's point of view, there is nothing much to do except doing some basic configurations in the GUI for the first time and hitting few buttons to get the complaints report. So the solution itself is very simple, fast, reliable, and out of box, where user can get the protocol complaints report within a matter of few clicks. So before jumping into the more detailed demo of the solution, I would like to cover what are the different components present in the solution. So we have a certain software and hardware piece involved here. So let's start with the software. So the item that we see in the left hand side is the software part that we have. So it contains a protocol validation software, and it internally contains many multiple items into it. So one is the protocol exerciser and debugger, which is something a similar protocol exerciser and debugger that you see in the market. So this helps the user to manually configure things and do the protocol validation manually. And also on top of it, we provide the script editor where the user can create automated test scripts. Again, a script in the sense it's just a drag and drop and GUI based configuration, and it's not on top of any programming language. So any user, even without programming language, can create automated test scripts using the software, and the script can be executed, and in the backend the complaints, test reports, and graphs are generated automatically by the software. And moreover, this provides automation APIs and DLLs that can be called in NI LabVIEW, Testan, C# or Python environment to automate the software on certain use cases, like say for example, if you want to run a particular protocol test across temperature, and the loop to control the temperature and all the business logic to control the temperature is available in Testan or in Python, you can just simply call this API into the loop and command this particular software to execute the protocol validation test from Python environment for each temperature value. So we can do much more beyond this using this APIs and DLLs, and this is just an example. So this is the software component that runs inside an PXI or a PC controller, and it uses the NI digital pattern instrument, either PXI 6570 or 71, which is an ATE class instrument with 100 MHz onboard clock. This instrument is used to build the any protocol waveforms, and we have the Soliton interposer board in between for the purpose of signal conditioning. So one of the main items that is taken care is the bus capacitance and parasitics other parasitics. So for example, if you take MIPI I3C protocol, there is a specification limit that the bus capacitance should be less than or equal to 50 picofarad. So interposer board takes care of those aspects. So this board, the instrument and the software acts as the controller, and it works with the DUT and talks to the DUT and takes back the response and do the measurements and create the reports. For certain specific measurements, we need an oscilloscope, and we do support both PXI oscilloscope and benchtop scopes. And software can automate the scope and get the waveform through GPIB or USB or interface, and it can post-process the data and get the measurements. So these are the important blocks that is available in the solution. Let's see a live demo of the MIPI I3C validation solution by Jake from NI. Over to you, Jake.
Once your new device has been designed and built, then comes everyone's least favorite step: extensive amounts of testing of the device's digital communication interface. In order to show you a demonstration of that today, I have here an NI digital pattern instrument inside a PXI chassis, connected to a Soliton interposer board to handle signal conditioning, then connected to an I3C enabled sensor. So now that we've seen the hardware, let's take a look at the software. Here on the opening of the PVS tool, you'll see the device configuration window. Everything in the PVS tool is project-based, and once you have your project configured, then you can configure the device profile, which I've started for my sensor. I'll first assign the digital pattern instrument that I have connected. In this case, it's the 6570 PVS that I've labeled here. And that device will emulate the controller instrument in my tests. Then I need to configure the interposer board, which I've already configured channel 3 to be connected to my DUT clock line, and channel 4 to the data line. Then I need to tell the software the I2C target address information, as well as the I3C dynamic target address. So for this device, that's 5C, and for the dynamic address, I'll use 9. I can also configure an oscilloscope if I'd like to, but for this demonstration, I won't use one. And now that we've got our device configured, I'll move over to the debug screen, where we can interactively do point and click measurements, and also talk to our device and ensure that it's working, and do a sanity check that our hardware connections are correct. In order to do that, I will go ahead and set up an SDR private read-write, and I will write to register address 52 with the data 50, for example. So when I write that data, and I read that data back, I see that I do indeed get the expected data, and that tells me my device is connected correctly and ready to test. So now that I'm ready to test, I'll move over to the Test Plan Editor tab. In this tab is where I will configure my own custom script. And so using the basic building blocks on the left here, I can drag and drop standard structures and functions that are common in the I3C standard to allow myself to create any custom script that I'd like, or I can use template scripts that come ready to go out of the box with the software. So as I scroll through the basic functions, you'll see similar I3C tests such as dynamic addressing and hot join. And for example, if I throw in a couple of these steps to my script, you'll see on the right, the configuration pane opens up, and that is where I will configure the specific settings of my steps to customize my script fully. So you'll see that I can go in and type my settings if I'd like, or if I just want to load up the default values for the standard, I can hit load defaults, and now those default values are ready to go. So that's a quick way to get your custom script ready to run. And on top of that, one other function I want to show is the custom command format. Most of the commands here are standard, but if you need to write something that's unique to your device, you can use the custom command format to start from a basic read or write command, apply that, and now if you want to change it up or add steps, you can add different steps, change the command throughout the step, and of course, change the bits as well. For the purpose of this demonstration, I'll go ahead and open up a pre-configured demo script that I wrote beforehand. And in this script, I'm going to sweep through two different parameters. I'm going to do a compliance check of the clock frequency, as well as a compliance check of the setup time parameter. In the clock frequency step, I'll be sweeping through the parameter frequency. I'll sweep from a nominal value to a minimum value, and then a nominal value to a maximum value, which I've configured here, all of those parameters. I've told the software to stop on a failure. And on that first failure, I want to go back and do a fine sweep. So I'll move back to the last pass value and using a 10 kilohertz step, perform a fine sweep so I get a more precise data point of the device failure. I'll also run a compliance check to compare this parameter with the device protocol standard to make sure that it is indeed in compliance. I want to call out here that as you see similar steps throughout a script or the exact same step, the parameters will show up at multiple points. So for instance, the configure I3C bus timing step shows up multiple times in this script. And if you look closely, some of the parameters are highlighted in blue text, whereas some are in black text. The blue text just means that that parameter is linked to a parameter file. If I go up here, I can see all the parameter files I have available to use, and I can create custom ones if necessary. And I can also open them up to see the values associated with each parameter. So when I link a parameter to the parameter file, what that means is that if I change that parameter value in the file, everywhere that that parameter is linked will change. So if I change this T-low parameter to 400, for instance, you'll see that it doesn't change in a place where it's unlinked, but if I go to a linked step, you'll see that it did indeed change to 400. So if I want to link this parameter to the parameter file, I'll now have all of my parameters in this sweep connected to this parameter file or list of global variables. And now I'm ready to run the test. So this is a big time saver when you want to change the value of a parameter throughout your entire script or project, but you don't want to go in and manually retype the values. So now that we have the test configured, we're ready to run our script. So we'll go over to the Run Screen tab. And from here, I can choose any of the project scripts that I've created or use the out-of-the-box template scripts. And I select the parameter file that I want to apply to my test. Before I run the test, I can add any other device detail information that I desire, such as a serial number or metadata, such as temperature or humidity or other points you care about for your test. So once I have that information entered, I'm ready to run the test. I'll click Run Test, and on the bottom here, you can see the waveform plot updating in real time as the test is run. It contains both the data and clock line information, and you can also look at the results table and inspect the results in real time as well. I can pause the test as needed or abort the test if I'd like, and I can also set breakpoints before the test if I want to manually select where I want to pause the test. As the test wraps up here, I'll point out that you can look at the data from the test in an automated generated report folder by clicking the report folder button and see that all of the data is saved here in CSV file format for later analysis or for inspection of your data. But if you want to interactively look at the data, you can click over to the report folder. And here what you'll see is the data on 3 different levels. The highest level is the compliance summary data, where you simply see the sweeps that you configured and the parameter values that you swept through, as well as the pass-fail information. Now, if I want to look deeper into these tests, I'll right-click a sweep and then hit Communication Iteration Data. So what that does is steps into every iteration of the sweeps that I set. And so now I can see the parameter value for each iteration, all the different frequencies, as well as the timing frequencies and other timing steps and other parameters that I used. I'll also see the pass-fail information here. And if I want to look even deeper on what failed, I'll then select a step that failed and go over to Communication Data, where I can see every command that was used in the test. So from here, I can see the parameter configuration file, I can see the parameter value that failed, and I can see the data that was read or written to see what went wrong. Here, I see on this step, I was expecting read data of 10, but instead I got 0. So that tells me that the communication failed. Now, if I wanted to put this device in this state and interactively debug, I have that option by selecting the data, right-click, and navigate to Debug Screen. So that brings us back to the debug screen we looked at earlier, and that loads up the parameters from that failure case, and now I can interactively debug and put the device in this failure state to figure out more information on what's going wrong. So if I were to run this step using those same parameters I just loaded up, we'll see that it fails and we do not get the expected data. Now, by changing some parameters and going back to a known working state, I can write that data again, read, and pick up a pass value. So let's try 12 megahertz, and there is the expected data. So now we know the device is in a good state. Now the PVS tool you can stay in this interactive window, or you can move your configuration over to test stand or another test sequencer and run automated tests that way. So for instance, I'll open up test stand, and here I have a file written to sweep through different set temperature points, and at each temperature point, we're going to run that same demo script you just saw, and so we'll collect data across a variety of temperatures. So I'll go ahead and run the test. And once I do that, I'll click back over to the I3C PVS tool. And from here, you'll see the exact same window. The test will run through all the different step points. And as it runs through, we can look at the data, we can look at the results table, we can pause and play as we like, or we can just let the test run. This test will take a few minutes to run, so I'll go ahead and jump to the end of the test. All right, now the test is finished, and I'll click back over to test stand, where I can see an automatically generated report that will contain the information from my test for all the different temperature set points in my suite. On top of support for test stand, the PVS tool also has support built in for C# and Python.
So thanks, Jake, for the wonderful demo. So on the whole, what value user would get while using this solution is the very important value is reducing the protocol validation time, which generally takes a few weeks using the protocol exercises available in the market to just few hours using our tool. So this increases the RTM for the user. Then with the rich GUI features, it is easy to test the corner cases, glitch recovery, and communication errors with our solution. And with the APIs that we are offering, it helps the validation engineers to easily integrate the solution with their existing automation infrastructure, so that their overall validation workflow doesn't change even if this protocol validation software is plugged in new. It's easy to build the custom test cases for your chip using the script editor that the solution offers. And with the interactive debug GUI, detailed and insightful reports, the debugging and reproducing the failure test cases becomes more easy, and user can easily debug any bugs in the interface and fix them easily with our solution. So these are the key value proposition that this tool offers, and as a user, you can experience even more values when you start using this tool. And again, all this benefits doesn't stop only with MIPI I3C validation. The same hardware solution can be taken to other protocol validation like I2C, SPI, SPMI, RFFE, and beyond. And moreover, the digital pattern instrument is an ATE class instrument that can be used for other digital testing apart from protocol validation like digital library test systems. So scaling this solution is very easy, and it's again based on the PXI scalable PXI architecture, which helps the user to easily scale this solution to other applications as well. So here are the certain testimonials that we have got from the existing users who is using the solution for a while, for past few years. So I will highlight few important points out from here. So this solution is an unified test platform that takes only 15 minutes for the setup, easy to learn. It has a structured and intuitive GUI. It has helped the customers to save $100,000 of NRE in the first year of application. The support from the Soliton support team to solve the issues or getting familiarity with the tool is in timely manner, and the customers are feeling really happy to recommend the products to the other groups within the company. So these are the certain feedback that we have got from our customer, and there are a lot of customers using this solution and they're happy with the protocol validation experience that they are gaining with this solution. So what's new? So we have recently launched MIPI RFFE target validation solution, MIPI I3C controller validation solution to validate the controller devices, and also we have a solution launched to validate the I2C controller devices. So these three are for the protocol validation space. And as Mike mentioned earlier, we have recently launched protocol analyzer, which helps the user to analyze the protocol, sniff the protocol bus, and understand what's happening there, to make the measurements over there. And we do support I2C and MIPI I3C protocol as a first step for the protocol analyzer. So these are the new solutions we have launched to the market apart from the existing solution. So with this, I will hand it over to Mike for the wrap up. Over to you, Mike.
All right, thanks, Saravana. So to wrap things up and summarize, what you've seen today is a complete turnkey solution for protocol validation of target devices. This is for not only MIPI I3C, but some of the other protocols we mentioned, including I2C, SPI, MIPI SPMI, and MIPI RFFE. It includes high-performance PXI instrumentation for the digital communication and even oscilloscopes for those additional measurement types Saravana mentioned, as well as the turnkey software needed for both interactive and automated compliance testing of your digital interfaces. So if you're interested in learning more, there are some tools built into the webinar tool where you can contact us, download the slides, or ask a question. But I also included some links in the slides. So if you're reviewing those slides later and want to visit the solution page for the protocol validation solution, that link is there. There's also a link to our other semiconductor solutions and another contact us link in case you need to contact us after the webinar concludes. For now, we'll go ahead and transition to the live Q&A portion. So if you'd like to add your comments or questions in the chat box, we can answer you for those, or you can speak up and ask your questions verbally. So we'll do that now. Thanks.